Hey guys, welcome to day 6 of our journey to FANG companies. Unfortunately, due to a technical issue, I wasn't able to upload the original video. However, I'm going to do my best to sort of emulate the process through which I went in order to complete it. And see, this was question number 1443, called the minimum time to complete all apples in a tree. Goes a little something like this. Given an undirected tree consisting of n vertices, numbered 0 through n minus 1, which has some apples in their vertices, you spend 1 second to walk over one of the edges of the tree. Return the minimum time in seconds you have to spend to collect all apples in a tree. Starting at vertex 0 and coming back to this vertex. The edges of the undirected tree are given in an array of edges where edges 1 is, or edges I is the link between nodes A and B. It means that there exists an edge connecting vertices A and B. Additionally, there's a Boolean array has apples where has apples I is true, meaning that vertex I has an apple. Otherwise, it does not have any apple. So basically, we have a tree that's represented as a set of undirected edges, critical to remember. And this tree, on this tree, each node can either have or not have an apple. That apple or whether the node has an apple or not is denoted by the has apple list of Boolean or of Boolean values. So example number 1. Oh, and obviously we start at the 0th node and traverse the whole tree in a DFS fashion, deep first search, and find how much time it would take for us to get all the apples, to collect all the apples. The example here, and the red nodes are colored in according to whether they have an apple or not. So the red ones have apples, the white ones don't. And you can see that some of the white nodes are actually in the path of the path that we need to take because their child or children have apples. So nodes 3, 6 aren't in that path because none of their children have apples, but nodes 0 and 1 are, even though they don't have apples. Let's look at this case a little bit more thoroughly. We have this edges list of 0, 1, 0, 2, 1, 4, 1, 5, 2, 3, 2, 6, 0, 1, 0, 2, 1, 5, 1, 4, 1, 5, 2, 3, 2, 6, and the output is 8 because 1, 2, 3, 4, 5, 6, 7, 8. Pretty simple. I would start the recursive definition as such that if I'm on any sort of node, the time it would take to collect all the apples of my children would be the sum of all the apples from the left subtree, the sum of all the apples on my right subtree. Conditionally, if there are no apples on my children's side, I have to then start checking whether I have an apple or not. Because if I do, then I have to return that I have an apple, and if I don't, the final result is 0. So first step is to construct a tree, a representation of this tree. And I'm going to show you how I did it the first time, show you the mistake that I made, and the solution that I found to actually accommodate that missing edge case. So the tree would look something like this. It's a dictionary where the key would be the node and the value is an array of its children. So for edge in edges, I'm going to say that parent is going to be edge 0, and child is going to be edge 1. And then a simple condition to make sure that if my tree, if let's say parent not in tree keys, then I'm going to say that tree, and I'm going to initialize the value with an empty array. I'm going to initialize the parent key value with an empty array, and then I'm going to say tree parent append child. So in the case that I'm registering a parent node for the first time, I'm going to make an empty array for the value and append its child. In the case that a parent already exists, I'm just going to append its child. And we can see that the tree is actually created correctly by running this program, clicking run. And although the result is an error, the S standard out is completely representative of the tree. 0 has children 1 and 2, 1 has children 4 and 5, and 2 has children 3 and 6. Perfect. Now that we have a representation of this array, let's define the recursive function, the recursive DFS function that's going to be called over and over again. So we need to pass in the current node. We also need to pass in the has apple array. And let's see. Right off the bat, that seems like that is it. I'm sure that we will go on adding more parameters as time goes on, but let's say now that we are at the or sorry. Well, in recursive definitions, you often try to find the edge case of which or the case in which this function has to exit the quickest. And in my case, the function will exit the quickest if it's looking at one of the leaf nodes. So the leaf node would be defined and caught by this if statement. So if current not in, and this is my first thing that I'm going to add, the tree. I forgot the tree. If not in tree keys, then I'm at a leaf node. The leaf node can be of two different types. It can be either contain an apple or it cannot contain an apple. The way that we can do that pretty quickly is we can say has apple, right? And the has apple array actually contains all of the Boolean values. So here, notice this, that if we have an apple, the parent node has to append value 2 seconds to its path. So we can say 2 if has apple, else 0. This way we have the condition that if we're stuck on the leaf node or if we have reached the leaf node, our timing is going to be correct for that, whether it has an apple or not. Next, we have to consider other scenarios where we are in a transient node or a branch node. This branch node will be something along the lines of this. Well, I have to know, I have to calculate the time that it takes for all of my children I have to calculate the time it takes to collect apples from all of my children. So I would say that the total time, start off at 0, and then say for child and children. Okay, let's children array is going to be the tree current, and for child and children array, I'm going to say that for child and children array, I'm going to say this: self DFS child tree has apple. So this is my recursive definition um, for finding whether I have an apple or not, right? And let's see, is that enough? Once I have, no, that is not enough because currently we are not capturing the situation where a transient node, one that's in between the root and the leaf, has an apple. Here, what we can do now is use this total time variable and has apple to calculate which scenario would give us would start or give us another 2 seconds to our flow. So let's see, what are the different scenarios? I'm gonna start with a general truth table. So not has apple and no, not children, or not children not have apples basically is this, right? That would mean that children don't have apples. Um, I have an apple, spelled that wrong, and total time equals 0. I not has apple and not total time 0. And where both cases are true, not has apple and not total time 0. So in this case, if I don't have an apple and my children are is equal to 0, I'm going to return 0, right? Because it means that this node is blank, and so the parent node would actually receive that since I'm not in the path because none of my children have apples and I don't have an apple, I'm going to return 0. If I have an apple and the total time for children to take an apple is also 0, well, now I'm in the path. So I can say return 2 because I'm appending 2 more seconds um, to my path. Now let's see the third scenario where I don't have an apple, but my children have an apple. I have an apple, but my children. I don't have an apple, but my children have an apple. In this case, I have to return total time plus 2. And in this case, where not apple and not total time, I would actually return if, oh, I wrote the same thing. Wait, not, I have an apple and my children have an apple. Wait, I messed this up. Um, I don't have an apple, but my children have an apple. No, I don't have an apple and my children don't have an apple. I have an apple. So, sorry, neither one has an apple. I have an apple, my children don't have an apple. So 1, 0. I don't have an apple, but my children have an apple. I have an apple and my children have an apple. So where's the not? 0, 0, 0, 1. Yeah, 0, 0, 0, 1. Uh, total time plus 2. So what you can actually notice is that these should be switched. I don't have an apple, and my children just don't have an apple. I 0, 0, 0, 1, because I'm in the path. 1, 0. I have an apple, but my 0, there we go. 0, 0, 0, 1, 1, 0, 1, 1. Yep. The thing here is that what you can notice is that if in this case total time is equal to 0, I can just say that total time plus 2 because it's not going to affect. So the only scenario which I really have to watch out for is that neither me nor do my children have an apple. So I'm going to say this in an if statement. If not have apple and total time is 0, return 0. Otherwise, return total time plus 2. Now let's see, has apple. Current and right off the bat, this should work. Now, this should work for most cases. I'm gonna run this and see. Uh, the one thing here that I have to watch out for is since I am starting this almost from if I was to start this from 0, I would have to watch out that my that the person that I'm returning to, or the node, the fake node that I'm returning to, is actually going to receive another 2 in the case that any of its subtrees has an apple. So I would have to subtract 2 from the result. So the returning statement would be self DFS current tree and has apple. And let's run this, see how wrong we are. We should be off by 2, and we are. So if, let's see, how does the condition work here? That if, well, actually, no, let's go through the official way that I did it. I would just subtract 2. I would subtract 2 only in the case that, okay, so time. So I would say time plus 2 minus 2 if time does not equal 0, else 0. Okay, sweet. The thing is, if I was to submit this right now, we're going to get some funky behavior. We're going to get funky behavior with trees that are represented in a specific way. This specific way is edges that are whose from and to are sort of switched. So previously, we've seen examples of 0, 1, 0, 2, 1, 4, 1, 5, 2, 3. What you can notice here is that all of these the from edge or the from node is always higher than the to node. But in this case, the graph would look something like this, or the tree would look something like this. Mm, 0, 2, 0, 3. But then the 1 and the 2, do you see how the 1 and the 2 are switched? So even though the 1 is actually here, the the relationship between them is switched in the representation of the edge. The way to go about it is to actually overpopulate this tree representation. And how we're going to do that, overpopulate it means that uh, stop considering a parent and a child relation. Start thinking of them as just nodes A and node B, and say that if A is not in the node, then A, B, but also if B not in tree keys. So this way, we're saying that I don't care whether this is a portion of the question where we worry about there being a direction. And it's said, if you remember, that it's undirected. So in this case, we don't care about um, the direction of which the tree is formed. We worry about all of the connections. We worry about the parent to child, the child to parent. What's going to help us stay on the right path of the DFS is that we're going to start from the zeroth um, node. And once we start traversing, if we are looking at this node, we're going to actually keep track of the parent of the place that we came from, and we're going to skip that traversal. And how that's going to work is like this. This is my current node, and this will be my parent node. The parent will be here. And let's see. So here, if current, and it's a parent, then continue. So I'm not ever calling this function if my current child, child is actually my parent. Uh, Current child current. So this way, we're starting off from a node that doesn't exist anywhere in the tree, so it's never going to be parsed. We're calculating the time, and then we're making sure to exclude a backwards path to the parent. And let's see. Let's see what I did here. Da-da-da-dum. Tree B, forgot. Okay, now let's submit this and let's see how if this works. Sweet, worked. So this is our first successful submission. Awesome. We have about 7 minutes left. In reality, this question took me probably a bit longer the first time that I solved it. But actually, in day 7, which actually I just filmed before this, the representation of the tree is very similar to the way that it's represented here. Actually, it's identical, and even the test case was failing to me on this on the same thing. I realized that the solution of building the tree is pretty much the same. It must be some sort of standard. Um, yeah, let me know if maybe a visual representation of what that overpopulation of the tree is needed, because I would be happy to do that. Now let's probably take a couple of seconds to see what the better solutions were. Um, so min time initialized one function. Wow. Okay, so initialize a array of, yeah, I never used that n, but we initialize a -1 array of parents, and for each edge in edges, parent-child edge. That's almost like a split operator or an a spread operator. There we go. Parent-child, that's done. If parent of child is -1, so if it's never been seen before, then child, parent, parent of the child is parent. Else, yeah, I'm not really understanding what this purpose of the parents array is. It seems like he is, or they are a populating a array where they're doing a similar thing to what I'm doing, where the parents here they're defining the parent, the child. For a child, the parent is parent, but why for the parent? Why is this a child? Is this in the case that a child is not, if a child has already been, you know what, this is too confusing to me. I don't, okay. Okay, still initializing a -1 array of length n of parents and setting all the parents to A, setting all the child to parents. Child, parents. So with this array, if I pinpoint myself to a specific child, I can immediately find its parent. The problem here is that that's not always true because in the case that I showed you, the order of the nodes was essentially switched. Uh, so I'm missing something. Marking nodes for it if they have an apple descendant. Marking nodes for it if they have an apple descendant. For I in range, and this means that it's traversing it backwards, I believe. If has apple parent true. Yeah, if has apple true. Guys, this is a completely different approach, and I'm going to have to look at it a little bit further. But from my understanding, the more traditional approaches probably use a DFS search. Yeah, and I could have done this better. Yeah, I could have done this better, but they're all DFS solutions. So yeah, so the DFS solution is very acceptable, and I think that that's actually the more standard way of going. People that get into the 90th percentile, they're really killing it with that algorithm that I don't know. But yep, thanks for tuning in. Like if you like this content, and let me know in the comment section if I should do some more deep diving. All right, thank you. Have a good day. Bye.